I think as a civil engineer you are already familiar with the term cantilever beam, and the use of this cantilever beam in our daily life is limitless. Just for example, you can see in the picture, it's a very famous steel bridge in Howrah, and it's also based on a cantilever beam mechanism. Don't worry, I am showing you. Just consider these two as support. This is one support like this fixed support, and again this is another fixed support. Okay, and this is one cantilever. Here I have shown in red color, and this is another cantilever beam. Okay, and this is the simply supported beam rest on these two cantilever. And during construction you can also see here that this is the support, this is the cantilever part, and again this is the support, this is the cantilever part, and this simply supported beam will be rest on these two cantilever part. Not only that, in concrete construction you have seen this type of thing. This is also one type of cantilever beam. Okay, and in design of base plate I think you have seen the use of stiffener. This is also one type of cantilever. Well, in this video I will discuss how to analyze all type of cantilever beam with different type of loads. Okay, so let's start. By the way, if you are civil engineer, welcome to my channel. You can subscribe this channel to get videos on analysis, design and construction. So what is cantilever beam? Consider this as a beam, and this is the support, this is the free end. Okay, there is a specialty in this type of support. What? This support doesn't allow this beam to rotate or to move. In vertical direction, this restrains this beam to move. In horizontal direction, also this support restrains this beam to move. And again, also if you try to rotate this beam like this, or if you apply any moment here, again this support resists this rotation. So this is the specialty of this support, and this support is known as fixed support. So for any cantilever beam, there is only one support, that is your fixed support, and other end is free, there is no support. Okay, again let's see in the picture. Here you can see this is the free end, okay, and this is the fixed end. Again, for this bridge also, this is the fixed end. You can consider this as fixed end, and this is the free end where this simply supported truss is rest on. Okay, so this is known as your cantilever beam. Now this is time to analyze it. Okay, simply apply a load where like this. So this is our cantilever beam, and I've applied a point load here. This is known as a point load. Now what happened? When you apply this load, there obviously will be a reaction where at this support like this. This is the vertical reaction because you have applied vertical load, and there is a moment like this. Why this type of reactions are coming? Because when I apply load on this structure is in equilibrium, or this structure does not move. Now what is the condition for an equilibrium? To satisfy the equilibrium condition, there are three equations. What are they? The summation of vertical forces should be 0. So this is the downward force, obviously there should be an upward force. Again, summation of horizontal force is 0. There is no horizontal force. Okay, so we will not discuss about it. And last one is summation of moment is 0. So you can ask me, where is the moment? Well, if this is the support, when you apply a load like this, now stand here and stretch your hand like this. If I put a load on your hand, you will feel a bend here. That is the bending moment. Okay, so similarly, when I have put a load here, obviously there is a moment like this, and to counter this moment you have to produce a reaction moment like this, because this is a fixed support, and a fixed support does not allow you to rotate. Okay, so there are two reactions for this type of loading arrangement. Now in this video we have to learn how we can analyze these reactions, or how we can analyze a cantilever beam. So from this equilibrium equation we can find this reaction force. Let's find them. First one is summation of vertical force is 0. So let's assume that our upward force is positive and downward force is negative. This is our axis system. Okay, so this is the vertical direction. We will take positive in this direction and take negative for downward direction. Here we have applied point load P. This is downward and indicated in green color. So it is negative, and our reaction, let's assume first, this is upward. So it is indicated in red color and positive sign. Again, summation of horizontal forces should be 0. There is no such forces, so everything is 0 here. And last one is summation of moment is 0. Again, what is the moment produced by P here? Simply like this, and it is clockwise, and we will assume that clockwise moment is positive. That's why PL is positive. Okay, and we assume there is a negative moment here to counter this. For negative moment, this is negative and indicated in red M. Now we have to find the value of R and value of M or moment. Simply solve this equation, you get your reaction as P. So our assumption that upward reaction is coming is true. Again, the moment is PL and it is coming as positive. That means our assumption that an anti-clockwise moment is generated at the support is true. Okay, so you have already found how the reactions are coming and what are the values of this reaction. Now it is time to find the internal forces. Obviously, in a cantilever beam, it is not only our duty to find the reactions, but also we have to find the internal forces coming at different locations for a particular beam. Based on that, you will provide the reinforcement, or if you provide steel beam, you have to provide the depth properly. Okay, so let's find how we have to calculate the internal forces. Just assume again this beam, and we assume a section at the distance x from free end. So what is the reaction at this section at a distance x from free end? Well, let's assume the reaction is Rx. Again, Rx is upward. Well, then Rx plus downward force P or minus P should be 0 because the section is also in equilibrium. So Rx is coming as P, and similarly the moment in this section is coming as P into X or Px. Okay, so we have found already how the internal forces are coming in a cantilever beam. Okay, now if we have to find the internal forces each and every point, let's find them. At the very end, it is coming as P. Again, at a certain distance, again it is P. So continuously everywhere the force, the vertical reaction force is coming as P. What about the moment? We have seen at a distance x, moment is coming as P into X, or applied force into the distance of the section from the application of force. Okay, so at the very end, x is how much? 0. That's why the value of moment is 0. And at the support, what is the value of M? P into X. X is here the distance or L. So at the end or at the support, it is coming as PL. And in between you can find, let's say this is P into L by 2. So like that you can plot at each and every point of this beam how much vertical force and how much moment is coming. And this type of graphical presentation of internal forces are known by some specific term. What are the term? Well, the first diagram, this is known as your shear force diagram. Okay, this diagram provide you the shear force at any section. Let's say I have to find how much shear force is coming in this section. Simply calculate the shear force here. This value provide you how much shear force is coming in this section. Similarly, if I have to find how much moment is coming in this section, I will go there, and from this diagram I will calculate the value of bending moment in this section. Well, so this diagram is known as your shear force diagram, and this diagram is known as your bending moment diagram. Now this diagram have some specific sign. What are the sign? Well, for shear force we assume that clockwise is always positive. Now you can ask me how a shear force can produce clockwise moment or clockwise rotation. This is the applied force. Let's say this is this downward force. Again, this is in this section, this is the upward reactive force. We have already find it. Okay, so if I represent it like this, you can say they are producing a clockwise rotation. That's why this is positive. If this is anti-clockwise rotation, in that case the shear force is negative. Now what about moment? Whenever there is tension at top, this is negative, and whenever there is tension at bottom or smiley face, in this case there is tension at bottom, this is positive. In our case, what is happening? Say this is the applied moment and this is the resistive moment. So this member is trying to bend like this. This is not smiley face. Okay, so that's why it is negative. So like this we have already analyzed our cantilever beam for a point load. Now it's time to analyze it for a uniformly distributed load. You can assume that there are infinite number of point load like this, from this free end to this fixed support. Okay, so similarly again assume a section at distance x from free end. What is the force, or what is the vertical reactive force coming here, or what is the shear force coming here? Simply you can find from the equilibrium equation, it is coming as P into X, because each load is P, or the load for unit length is P. So we have to find the shear force for length X. What is the total load? Simply P into your X. Okay, from that the vertical reaction is coming as Px. And what is the moment? Simply assume the total load for this Px load is acting here at the middle, because this is uniformly distributed load, or this distance is simply your x by 2. So if you multiplied this load or Px with x by 2, you get moment as Px square by 2. Okay, now if you plot this, you can see that shear force is coming like this, or you can say compared to the point load where the shear force diagram was constant, it is varying, and it is varying linearly because the power of x is here 1. In case of point load, the moment diagram was like this, or it was varying linearly, but here it is varying parabolically. That's why here the diagram is like this. So this is the way you have to analyze any cantilever beam. Well, if you find this video useful, please subscribe it to get more this type of videos.